Welcome back to the Deep Dive. This is the show where we take a stack of dense, source material, geological maps, seismic reports, historical surveys, and really use them to unlock the secrets hidden right beneath your feet. And today, we're embarking on a really personal journey. We're translating a very specific, and I have to say, an amazing observation made by one of our listeners.
Indeed. We are focused today on western Ashley County, Arkansas, and we're zeroing in on the coordinates 33.1478, NAC 92.0206.
Right.
And this whole investigation, it started with K. Brad Barfield, who is exploring their own property using the newest USGS 3D viewer, specifically the Lidar hillshade imagery.
And K-Brad was surprised, and, rightfully so, by what that LiDAR stripped away and revealed. I mean, the ground beneath them, it looks pretty unassuming from the surface, but it is scarred, it's dramatic, and it's hydrodynamically complex.
It really is.
So thank you, K-Brad, for sharing your sources and your sense of discovery with us. You spotted something truly profound.
And that LiDAR technology, that's light detection and ranging, it really is our magic lens here. It ignores the canopy, it ignores the buildings, and it gives us the elevation of the bare earth.
The true shape of the ground.
The true shape. So when K. Brad looked at that stark hillshade model, they weren't just seeing a static plot of land, they were looking at a palimpsest.
I love that idea. It's not just a snapshot, is it? It's a history book.
Exactly. A surface that's been written upon and then erased and then overwritten by geologic processes over millions and millions of years.
And our mission today is to interpret those layers of writing. K-Brad's initial observations, they centered on 4 key geographical mysteries that we really need to validate and explain.
Right. They observed a distinct peninsula shape to their land. That was the first thing.
Okay.
Then they noted the sheer, the oversized nature of the valley cut by Brushy Creek. They called it a large something or other.
Which is a great description.
It's a perfect description. They also saw a dominant regional pattern of east flow. And then, and this might be the most insightful guess of all, they speculated about an ancient sea having once been there.
And we are going to confirm all of those intuitions. We'll use the geology of the region, from 40 million years ago right up through the last ice age, to explain why your land is so stable, K-Brad, why those valleys are so oversized, and why your backyard is, well, quite literally, standing on a fragment of the continental shelf.
So let's start with that first feature K. Brad saw immediately. The high ground itself.
The peninsula.
Let's start exactly where the listener started, with that structure bounded by Brushy Creek and Bell Branch. And K. Brad, your observation that your land occupies this distinct structure is absolutely confirmed.
It's not just a gentle slope.
No, not at all. This is a profound geomorphological feature.
And it's not just an ordinary hill either. It has a very specific identity that speaks to its age and its stability.
That's right. Geologically, this high ground is what we call an interfluvial divide. That term, it just means it's the ridge or the high platform that's situated between 2 drainage networks, in this case, the 2 creeks on either side of the property.
Right.
But what makes it so important is its stratigraphic identity. It's a surviving fragment of the Prairie Terrace.
The Prairie Terrace. Can you elaborate on that? Why is that particular formation the key to understanding the stability of K. Brad's land?
Think of it this way. The Prairie Terrace is a Pleistocene ala formation.
Whoa, okay, break that down for us. Pleistocene ala formation.
It's jargon, I know, but it just means it's a body of sediment that was laid down during the Ice Age epoch.
Ah, okay.
And it is the anchor of stability for your property because it represents a far older, much more robust surface than all the easily eroded clays and silts you find down in the valleys.
So if the ground around you is kind of a waterbed.
The Prairie Terrace is a concrete foundation.
Exactly.
A concrete foundation laid down by a massive ancient river, as you said. So let's pin down the timeline. When we say Pleistocene, how old are we talking for this specific platform? The Prairie Terrace primarily dates to the late Pleistocene, so it covers the Sangamonian interglacial and the early part of the Wisconsin glacial stages. We are looking at a formation laid down somewhere between, say, 80,000 to 120,000 years ago.
Wow.
Geologically speaking, that is ancient stability in a region that has otherwise been incredibly dynamic for the last 10,000 years.
So 100,000 years ago, what was happening in this region that allowed such a massive, stable platform to be built? I mean, it clearly wasn't the work of the little streams we see today.
No, this is where the sheer scale of the Ice Age becomes the architect of the landscape. The Prairie Terrace is a classic valley train deposit.
A valley train.
During peak glacial periods, the ancestral Mississippi and, crucially for this spot, the ancestral Arkansas rivers, they weren't just rivers. They were these systems that were just utterly swollen with glacial meltwater or outwash, pouring south from the ice sheets up north.
We often think of the Ice Age as just being cold, but the amount of water moving around must have been unimaginable.
It was catastrophic in scale. These rivers carried immense volumes of water and sediment. They weren't flowing in tidy single channels like the modern Mississippi.
Right.
They were massive, disorganized, braided systems.
So multiple channels all shifting around.
Multiple, shifting, shallow channels that just swept across the entire valley floor. And they were choked with coarse sediment sands and gravels that the glaciers had ground up in the north.
So the river was essentially just carpeting the entire valley with successive sheets of this sand and gravel.
Exactly. This process built the valley floor up to a significantly higher elevation than where the rivers flow today. K. Brad, your land is the preserved surface of this ancient elevated riverbed. It was once part of a continuous plain.
Okay, so if it was once a continuous plain, what happened to the rest of it? How did K. Brad's specific patch survive all the subsequent changes?
Well, that takes us to the second phase, incision.
Incision.
As the climate cycled out of the Ice Age, the continental ice sheets retreated and global sea levels fell dramatically. The rivers, now deprived of all that sediment load but still carrying significant flow, they gained erosive power.
So they started to cut down.
They began to entrench. That means they cut aggressively down into the very deposits they had just laid down.
Carving new, much deeper valleys.
Precisely. The peninsula is what we call an erosional remnant. The major channels, the ancestral Arkansas River system, they cut new, lower valleys on either side of the feature, scouring away the surrounding Prairie Terrace material over thousands of years.
And K. Brad's property was just left behind.
It was simply stranded between these two massive deepening cuts.
So if you were standing there 80,000 years ago, you were on a vast plain. But if you were standing there 10,000 years ago, you were watching the world around you just drop away into these massive new river valleys.
That's the chronological perspective. It survived the erosional purge, making it a chronological island, standing proud above the more recent chaotic sediments that were laid down during the Holocene. Right.
The stability that K. Brad senses on their property is directly proportional to the age of this platform.
That's a fantastic image. An island of 100,000-year-old stability surrounded by land that's maybe only a few thousand years old.
That's it in a nutshell.
Okay, so now that we've established the peninsula as this stable platform, let's tackle the other side of the equation, the massive valley surrounding it. K. Brad's instinct that the valley cut by Brushy Creek was a large something or other is really key here.
Oh, that instinct is absolutely validated by the geological record and the Lidar imagery. We can confirm that the valley occupying Brushy Creek was indeed shaped by an ancient hydrological giant. Specifically, an ancestral course of the Arkansas River.
So the little creek running through that valley today is just a ghost of a truly enormous river. What visible evidence on the Lidar image tells us that the ancestral river was so much larger?
Well, look at the sheer geometry of the valley floor. The Lidar reveals these incredibly clear meander scars.
Meander scars, okay. There are these curvilinear ridges and swales, sometimes called scroll bars, and they mark the former positions of the river channel. These scars are huge, looping features that are simply out of scale with the flow of Brushy Creek today.
So the size doesn't match.
Not at all. There are the unmistakable fingerprints of a river with a width and a discharge that was hundreds of times greater than its modern occupant.
So the modern creek is essentially a tiny, low-rent tenant occupying a gigantic antique mansion.
That is the classic description. Geomorphologists classify Brushy Creek as an underfit stream.
Underfit?
It means it's a stream that is mismatched to its valley. It's flowing through a channel in a floodplain it could not possibly have created, nor could it fill it except maybe during the absolute highest of modern floods.
Right.
The size of that valley directly correlates to the immense volume of Ice Age meltwater and continental runoff that once surged through this corridor.
So let's get specific about this ancestral course. The sources point to a relatively recent history for this specific valley, perhaps tying it to the shifting habits of the Arkansas River.
Correct. While the overarching valley was defined earlier, the latest and most identifiable carving phase points to the ancestral Arkansas River, potentially part of what's called the Stage 3 Coles Break Meander Belt.
Coles Break Meander Belt. And how old is that?
This places the river here approximately 6,000 to 4,500 years before present. So in geological time, pretty recent.
And when the Arkansas occupied this course, it was a dominant, powerful system, curving huge arcs across the landscape.
Oh, yeah.
And the presence of this huge river directly explains the shape and the boundary of Cape Brad's high ground.
Precisely. As the river carved those wide looping meanders, it constantly attacked and eroded the western edge of the high Prairie Terrace, the very edge where Cape Brad lives.
Okay.
This aggressive lateral erosion created the distinct steep scarps or bluffs that define the high ground. The peninsula is a remnant protected by its elevation, but it's defined by the erosive power of that ancient river.
But the sources also suggest that before the Coles Break River, there were even bigger things happening. Cape Brad might have thought the valley was pretty large, but it was perhaps excavated by something truly colossal.
That's right. Now we have to zoom out to the age of the megafloods. We're talking about the Deweyville complex.
The Deweyville complex.
If the Coles Break River was large, the Deweyville flows, which peaked during the late Pleistocene, say 30,000 to 60,000 years ago, were hydrological super rivers.
Super rivers. What kind of discharge are we talking about here?
Estimates suggest the Deweyville flows had discharges 2 to 5 times greater than the modern Mississippi River.
2 to 5 times the Mississippi, wow.
They were continental-scale drainage events. Their scars are these sweeping, massive arcs cut deep into the older Prairie Terrace surface.
So the Brushy Creek Valley.
The most likely scenario for the Brushy Creek Valley is that it's a composite feature. It's a gigantic trench that was first excavated by a Deweyville megaflood, which was then later reused and slightly modified by the Holocene Arkansas River of the Coles Break Belt.
This stepwise decline in river size gives us a visual signature on the landscape. Can you describe the staircase topography that a LiDAR viewer might look for?
Certainly. If you stand on the high Prairie Terrace on your land and you look down toward the modern creek, you often don't see a single smooth slope.
Okay.
Instead, the landscape drops in distinct steps. The highest step is the Prairie Terrace. You might then descend to a slightly lower, very broad, flat surface. That intermediate terrace is often a preserved, partially eroded Deweyville surface.
I see.
And then finally, you drop into the narrow, modern flood bottom, which is filled with recent Holocene clay. That staircase records the literal stepwise decrease in the volume and power of the regional river system over the last 60 millennia.
It's a timeline written in elevation. Yeah. That's fantastic. Now let's look at the two modern creeks, Brushy Creek and Bell Branch, and how they actually flow. They have a very specific, almost strange behavior common to this area.
They are textbook examples of Yazoo streams.
Yazoo streams.
It's a concept named after the Yazoo River in Mississippi, and it perfectly describes the hydrology of the lowlands adjacent to a major river valley. Okay, Brad, if you look at the flow paths of Brushy Creek, you'll notice it flows parallel to the main ancestral river course for a long, long distance before finally joining it much further south.
So why are they so reluctant to join the main channel immediately? Why do they flow side by side like that?
It's because the main river, the ancestral Arkansas, built its own defensive wall.
Oh, wall.
When any major river floods, it drops its heaviest sediment right along its banks, and that forms these large elevated ridges known as natural levees.
Right, I've heard of those.
And these levees were simply too high and too wide for the smaller local tributaries, the water draining off the Prairie Terrace, to breach directly.
So the local drainage water was trapped.
Exactly. The local drainage coming off the high ground was forced to pool in the low spot, what's called the rim swamp, trapped between the high river levee on one side and the terrace wall on the other.
And that became the Creek Valley.
That elongated low spot became the Brushy Creek Valley, and the stream flowed opportunistically down valley, just seeking the lowest point to eventually merge with the main system.
So this mechanism is why Cape Brad's land is defined by two different erosional events.
That's right. On the Brushy Creek side, it's bounded by the steep, aggressive scarp of the ancient Arkansas River. And on the Bell Branch side, it's bounded by the simple, local incision of a much smaller tributary.
We've thoroughly analyzed the surface of the land, defined by ice and water over the last 100,000 years. But now we take the deep dive, literally. Cape Brad's final great intuition was about a sea, They asked if the land might have been underwater back when there was a sea around us.
And that intuition is absolutely correct, and it points to the deepest layer of geological history underlying Ashley County. The foundation of your property, K-Brad, was indeed laid down by a warm, shallow sea during the Eocene epoch,
Holocene. And that's
approximately 35 to 45 million years ago.
40 million years ago. That requires a huge shift in our mental map of the continent. What did the geography of North America even look like then?
It was radically transformed. The Gulf of Mexico's coastline was situated far, far to the north. It extended deep into the continent, encompassing much of what is now southern Arkansas and central Louisiana.
Wow.
K. Brad's property, sitting on the border of the West Gulf coastal plain, was situated right in the massive structural depression known as the Mississippi Embayment. And this trough allowed the ocean to repeatedly flood what is now dry land.
So if K. Brad were standing at their coordinates 40 million years ago, they'd be looking out at the open ocean or maybe wading through a vast, muddy estuary.
Precisely. And the source material highlights two specific layers that record this transition, preserved directly beneath the Prairie Terrace sands you live on.
Okay, let's start with the lower layer, the Cockfield Formation.
The Cockfield Formation records what we call a regressive phase, a period when sea level was slowly falling or when continental sedimentation was outpacing the rate of sea level rise. These sediments are characterized by lignitic sands, silts, and clays deposited in vast deltaic swamps, tidal flats, and shallow lagoons.
That sounds like a tremendously rich, but very swampy environment.
Oh, it was. It was dominated by huge, ancient Eocene forests and cypress-like trees. The crucial marker here is lignite.
Lignite, like a low-grade coal.
Exactly. Historical surveys confirm it exists below the surface of Ashley County. Lignite is simply fossilized, compressed peat, the organic remains of those enormous swamp forests. It proves that the area was once a huge, carbon-rich wetland right near the coast.
Okay, and what about the layer above that one?
Above the Cockfield, we find the Jackson Group. This sequence marks a major transgression.
So the sea is coming back in.
The sea level is rising again, flooding those swamps and bringing truly marine conditions back to the area. These are fossiliferous clays and marls, recording a warm, shallow sea that was just teeming with life.
What kind of life defines this deep marine layer? What would we find in there?
Well, the equivalent strata in neighboring regions are famous for the remains of primitive whales, like the Basilosaurus.
Whales. In Arkansas.
Imagine a sea where ancient serpentine whales swam over K. Brad's property. These sediments represent the true continental shelf, recording millions of years of life and sedimentation before the entire region was uplifted and exposed to the atmosphere again.
Then we have specific local evidence too, right? That confirms these layers are right there waiting to be discovered.
We do. Historic well logs from nearby towns like Hamburg provide the definitive stratigraphic sequence. When drillers pass through the surface layers, the Pleistocene sands and gravels, they hit the blue or light gray clay with abundant leaf impressions and microfossils at deeper levels.
And that's the telltale sign.
That characteristic blue clay is the immediate signature of the Eocene marine or estuarine environment. It's the smoking gun.
So beyond just confirming the deep history, this Eocene basement layer has a crucial function today, long after the water retreated.
It dictates the movement of water even now. These compact, clay-rich Eocene formations, specifically the deep parts of the Cockfield and the Jackson Group, they act as an aquitard.
Aquitard.
They are nearly impermeable to water flow. We refer to this as the marine seal.
The marine seal. And what does that mean for the water beneath K. Brad's property today?
It means that groundwater that filters down through the porous Prairie Terrace sands can't just keep going and is forced to move horizontally along the top of that ancient Eocene layer.
Okay.
This compact basement controls the hydrogeology of the entire region. The stability of the high ground, its internal drainage, even the source of the deepest drinking water, the Cockfield Aquifer, are all defined by the sediments of that long-vanished sea. The foundation of the land is literally resting on a massive, solidified layer of ancient seabed.
We've moved from 40 million years ago up to the age of the mega rivers. Now we need to shift focus to the surface, the microfeatures that K. Brad's Lidar imagery must be showing in sharp relief. Let's talk about the actual dirt that makes up the peninsula.
Excellent point. We move from the giant architect to the actual construction material. The dominant soil type on the Prairie Terrace, the high ground, is Callaway and Granada silt loams, and the core component of this soil is loess.
Loess, wind-blown silt, basically dust. How did a deep cap of dust get deposited on top of a riverbed in Arkansas?
It's a spectacular feat of geology. Remember those colossal braided river systems of the Pleistocene?
Right, the ones choked with sediment.
Exactly. They carried massive loads of sediment pulverized by the northern glaciers. But these rivers were highly seasonal. In the winter, when the meltwater slowed or stopped, the huge, shallow riverbeds would dry out, exposing vast plains of extremely fine, light-colored sediment.
And then the wind would just pick it all up.
Precisely. The winds would sweep this glacial flour, this silt from the exposed braided plains, and deposit it as a thick blanket across the adjacent uplands, including the Prairie Terrace. Your land, K-Brad, is constructed not just from river deposits, but literally from the dust storms of the Ice Age. This lavus cap can be many feet thick.
That's a fascinating lineage. Ice grinds rock, river carries it south, and wind builds the final stable platform. But this specific loess soil, it has a defining and kind of problematic characteristic that impacts everything from building to farming.
That is the fragment. This is perhaps the single most important physical characteristic of the Prairie Terrace landscape.
The fragment.
A fragment is a dense, brittle, cemented layer, often found only about 20 to 30 inches deep, just below the surface soil horizon.
How does that form, and why is it so brittle and impermeable?
It's a chemical process driven by millennia of seasonal water movement. Over time, clay, iron, and silica leach downward from the surface soil, and they accumulate and cement this layer together. When it's wet, it's firm and hard. When it's dry, it's brittle like concrete. Crucially, it is nearly impermeable to water.
And what are the immediate practical consequences of living on a fragment?
It creates an extreme high-contrast seasonality in the soil. In the winter and spring, rainwater hits the fragment and it can't drain vertically downward.
So it just sits there.
It results in a perched water table. The ground becomes soggy, saturated, and mushy very near the surface. This is the source of the modern water issue on the property. It's ponding, not flooding from the river.
So the land is too wet in winter. What about in the summer?
In summer, the fragment acts as a barrier. It prevents capillary action from drawing deep moisture up to the surface roots. So paradoxically, the soil becomes prone to severe drought conditions right near the surface, even if there's moisture trapped below the pan. This dual nature defined the ecology and frustrated early attempts at intense agriculture on this high ground.
Now, for the truly mysterious features that LiDAR often highlights, the small circular helix, the bumps or domes visible on the surface.
Yes, the mystery of the mounds. On the Prairie Terrace, these are classically known as prairie mounds or pimple mounds. Their origin has fueled geological debate for well over a century because they're so uniform and so abundant.
If they're so common, why is their origin still a question mark?
Because they're difficult to connect to a single process. One leading theory, the Nebka theory, suggests they are coppice dunes.
Okay.
This theory posits that during intense mid-Holocene drought periods, when the area may have been more of a semi-desert grassland, wind-blown loess silt was trapped by clumps of persistent vegetation, creating these small, permanent dunes.
That paints an image of a huge, dry, dusty plain.
It does. The other strong local theory connects them back to that fragipin we just talked about, the fossorial rodent theory. Specifically, pocket gophers, seeking dry ground above that seasonally soggy perched water table. Over millennia, they continuously excavated soil and built their homes, these little mounds, as permanent dry islands in a wet field.
So whether it was wind or gophers, these mounds are a sign of stability, but we have to pivot now to a much darker mimic. Mounds that are evidence of violence, not stability.
We must make that crucial distinction and introduce the concept of sand blows.
Sand blows?
Sand blows are not natural soil horizons or biological structures. They're dramatic seismic features. They are vents of sand that have erupted onto the surface through a clay cap.
How does that even happen?
During a powerful earthquake, the intense shaking can cause subsurface layers of saturated loose sand to undergo liquefaction.
Liquefaction.
When this happens, the sand acts like a heavy liquid, and if there's a crack or fault in the overlying brittle clay cap like the fragipin or the Eocene seal, the pressurized sand and water erupt to the surface, creating a small volcano of sand, often forming a crater or a pile.
The presence of sand blows, or even the potential for them, means we are dealing with a significant underlying tectonic system.
Absolutely. The occurrence of sand blows ties us directly to the Saline River Fault Zone, or SRFZ. This is a significant, active, though sometimes understated, geological hazard that runs right through Ashley County.
And it follows that east flow that K. Brad noticed.
It follows a distinct northwest to southeast path. That east flow, K-Brad observed, is structurally controlled.
What evidence do we have of past activity along the Saline River fault zone?
We have concrete evidence from paleoseismic studies. Trenching sites in this region, like the historic Morgan and Golden sites, have revealed displaced strata and buried sand blow features. Geologists estimate that these features record multiple strong prehistoric earthquakes, likely in the magnitude 5.5 to 6.5 range, occurring over the last few thousand years.
So these were powerful events.
Powerful enough to cause widespread liquefaction, yes.
So the stability of the Prairie Terrace is being tested by underlying tectonic stress. And you mentioned that the fault might even control the shape of the river valleys we see today.
It's highly probable. River channels, being erosive agents, often take the path of least resistance. Fractured rock along a fault zone is easier to erode than solid rock or unfractured sediment.
I see.
The pronounced linear sections, or lineaments, visible in the Lidar for Brushy Creek or Bell Branch valleys are strong indicators that the course of these paleochannels, and subsequently the modern streams, is structurally controlled by the underlying ancient SRFZ. The land is a canvas painted by water, but the frame is built by tectonic stress.
It's clear that the geology, the Prairie Terrace, the fragipan, and the massive river scars didn't just create physical topography. It created specific ecological zones that dictated human habitation and resource use for millennia.
That boundary between the high, stable ground and the low, dynamic valley is called the ecotone, and it's the most important ecological feature of K-Brad's property. We can even use the General Land Office survey records from the 1840s to paint a vivid picture of this contrast.
Okay, so let's start on the terrace upland, the high ground where the house sits.
Yeah.
What did the surveyors describe?
The high ground was characterized by a distinct pine-oak-hickory woodland. Because of that fragipan soil, too wet in winter, too dry in summer, this was a pyrogenic ecosystem.
Pyrogenic meaning fire-dependent.
Exactly. It was dependent on regular, low-intensity fire. This fire, often set by Native Americans, maintained open, park-like stands dominated by shortleaf and loblolly pine and post oak. It was relatively open, traversable, and dry.
And what about the adjacent creek bottoms of Brushy Creek and Bell Branch? What did they look like?
They were the stark opposite. The GLO surveyors frequently described these lowlands as gloomy swamps or impassable. They were classic bottomland hardwood forests dominated by massive bald cypress, water tupelo, and dense thickets of canebrakes. So a dramatic contrast. A sunny, open savanna leading sharply down into a dense, wet, dark swamp.
A very sharp contrast. And this explains why the name Prairie Terrace is literal. Yes. The unusual seasonality caused by the fragipan, coupled with historical birding practices, maintained genuine patches of natural prairies or savannas on the high ground. The peninsula wasn't merely forest, it was an elevated dry island of open prairie and pine savanna that stood apart from the surrounding bottomland swamps. And this unique soil chemistry and history also supports rare and specialized plant life, making the area ecologically important today.
Absolutely. The influence of the underlying geology is visible even in the flora. The fault systems we discussed, they sometimes act as conduits, bringing up saline water from those very deep Eocene and Cretaceous aquifers.
Okay.
Where this slightly salty, high magnesium water seeps out, it creates localized barren spots known as saline barrens or slick spots.
And these support unique life.
They host extremely rare flora that can tolerate high salinity, such as geocarpin minimum, the tiny, federally threatened earth fruit. And furthermore, the overall mature, fire-maintained pine savanna, the native condition of the high ground, is the required habitat for endangered species like the red cockaded woodpecker.
So the geology supports the rarity.
It does.
Turning to human history, this ecotone made the peninsula an archaeological magnet. Why?
Well, for 10,000 years, if you were a human in this landscape, you needed three things: safety from water, access to resources, and flat, dry ground for settlement.
And the Prairie Terrace provided all three.
It provided the only consistently safe place for base camps, villages, and burial sites in a region defined by seasonal flooding and deep swamps.
And the ecotone itself maximized resources.
By settling on the boundary line, groups like the Paleo-Indian Dalton people and later the Caddo and Tunica maximized resource availability. They had immediate access to the dry upland resources: deer, hickory nuts, fire-adapted timber, and instant access to the rich lowland resources like fish, waterfowl, massive timber, and cane.
So K-Brad is literally standing on ground that has been prime real estate for human occupation since the last ice age.
It absolutely has been.
And this pattern continued into the historic era and dictated early land use.
When settlers arrived, the high ground provided the only logical corridors for the first roads and trails, allowing them to bypass the frequently impassable, seasonally flooded bayou bottoms. Later, when the massive timber resources were realized, the Prairie Terrace became a focus for systematic logging.
And LiDAR can reveal remnants of that logging era.
It can. LiDAR often shows the faint linear outlines of the dummy line logging trams, the temporary railroads used by companies like Crosset Lumber. They needed stable, high ground to lay tracks and haul the massive logs, and the Prairie Terrace provided that essential dry infrastructure platform.
Finally, let's revisit the water issue. The stability of this land protects it from external river flooding, but the internal hydrology is governed by the deep basement.
Exactly. The peninsula is critically important because it functions as a major recharge zone for the Cockfield Aquifer, that deep Eocene layer we discussed.
Right.
Rainwater that manages to penetrate the loess and bypass the fragment slowly trickles down to replenish the deep groundwater supply that the entire county relies upon.
So the stability of the land is a double-edged sword. It protected Cape Brad from the violent history of the river, but it saddles them with internal drainage limitations.
That's a perfect summary. The flood Cape Brad imagined is a geological memory from 6,000 years ago. The modern water reality is ponding, the nuisance of a high water table trapped by the impermeable fragile layer just beneath the topsoil.
Okay, we have covered millions of years of history. We've gone from primitive whales to wind-blown dust, and from mega floods to pocket gophers. Let's synthesize these findings and place the peninsula in its larger regional identity.
Geologically, Cape Brad's location is defined by its margin. It is West Gulf coastal plain, and it marks the definitive boundary of the chaotic, dynamic landscape to the east. The peninsula is a highly stable outlier of the broader Macon Ridge complex.
I love the metaphor you used earlier, an island of stability.
It is precisely that. The user lives on a high, stable island of Pleistocene loess and sand that is surrounded by a sea of chaotic, recently deposited Holocene river clays and silts.
Right.
This island of stability dictates the western boundary of the massive Bouffe-Tensis drainage network.
And this framework confirms Cape Brad's observation about the regional east flow.
Confirmed. The northwest to southeast orientation of the drainage patterns, so visible on the LiDAR, is the preserved trajectory of the ancient Arkansas River distributaries. This direction aligns with the overall regional dip of the Gulf coastal plain, which naturally slopes toward the axis of the Mississippi embayment and the Gulf of Mexico. Water has always flowed to the southeast here.
And finally, that critical connection between the Arkansas River and the Mississippi.
It's confirmed. The Arkansas River flowed directly past the house during the Stage 3 Coles Break phase. And while the main stem of the Mississippi was further east, the waters in that ancient Arkansas course were always functionally part of the greater Mississippi system, eventually dumping into the Bouffe Basin, the vast overflow region that ultimately drains into the Mississippi.
So the river flowing near the property was an inseparable part of the continent's largest drainage network.
That's right.
This has been an incredibly detailed journey. Cape Brad, let's confirm your original checklist of observations and questions armed with all this new knowledge.
Let's review the biography of 33.1478, nettage 92.0206.
Okay, first, Brushy Creek was once a pretty large something.
Confirmed. It is an underfoot stream occupying the channel carved by the ancestral Arkansas River, a system that followed a much larger mega-flood Deweyville Trench.
Second, I may be living in the middle of a peninsula when it was flooding.
Confirmed. You are living on an erosional remnant, an interfluvial divide of the stable Prairie Terrace. Your elevation ensured that during the periods of massive valley flooding, your land remained a dry, protected peninsula.
Third, Mississippi River or Arkansas River could have been flowing behind my house.
Confirmed. The powerful ancestral Arkansas River flowed there for thousands of years, and its output connected directly to the Mississippi system via the Bouffe Basin.
Fourth, back when there was a sea around us.
Confirmed. The Eocene marine sediments of the Cockfield and Jackson groups form the structural basement and the impermeable seal underneath the entire property.
And finally, fifth, east flowed here.
Confirmed. The regional drainage gradient follows the geological structure, definitively flowing northwest to southeast toward the Mississippi embayment axis.
Okay, Brad, this research, triggered by your curiosity on the USGS 3D viewer, reveals that your property is one of the most stable and long-lived pieces of land in the entire region. It has a staggering lifespan, from Eocene ocean floor to glacial riverbed to island refuge.
And that stability is the final thought I want to leave you with. We talked about all the violence that created your land, The massive floods, the tectonic stress, the intense winds. Yet, look at the smallest features the lidar shows.
The pimple mounds.
Yes, those tiny, fragile domes of wind-blown dust, potentially built by gophers. The fact that those minor features survived millennia of catastrophic glacial floods, shifting mega rivers, scorching prairie fires, and multiple documented earthquakes from the Saline River Fault Zone proves the extraordinary resilience of this specific patch of Earth.
Wow.
Your home is built on a monument to survival that has successfully endured every geological challenge the continent has thrown at it.
What an incredible biography for a piece of property. Thank you so much, K. Brad Barfield, for sharing your sources and your sense of wonder. We hope you enjoy viewing your geological history right there on the USGS 3D viewer.
Thank you for allowing us to take this truly deep dive with you.
And thank you all for joining us on the deep dive. We'll see you next time.